In this video, we're looking at velocity time graphs. The first question, the easiest question that somebody can ask, is simply to ask you to find the velocity at a specific time. So, for instance, what is v at t equals, say, 26 seconds. So 26 seconds, we come right up here. There's our point. We go straight across on the graph, and we see that the answer is v is equal to 5.0 meters per second. You just read it off the graph. If it's a velocity time graph, you read the velocity off the graph. When it's a position time graph, you read the position directly off the graph. Really easy to answer that particular question. So, again, continuing our work on velocity time graphs, this time someone says, for instance, find the change in velocity, or they say find the average acceleration. So let's say they say find the average acceleration from t equal 5 seconds to t equal 20 seconds. So the first thing we have to do is we have to locate the velocity at each one of those two times, at 5 seconds and at 20 seconds. And if we go down right here and we draw us a line straight up, looks to be right about here it hits, and then we come from there across. It looks like maybe it's a little bit more than 5, but close to 5. So maybe we said that the first V1 is approximately 5 meters per second. And then what we need to do is locate the second velocity in our problem. And that appears to be 20 seconds right here. We bring it straight up. It appears to be about right there. And then from there we bring it across. And it looks to be roughly 150 meters per second. So what is the average acceleration? Well, it is the slope of a chord. It's the chord from here. Oops. Let me undo that. Put my little ruler on here to that place right there. So I'm looking for the slope of the chord, and that requires me to find two things. It requires me to find delta t. Delta t here was 15 seconds, and it requires me to find the change in velocity, which is right here, and delta v. And delta v was 15 minus 5, which was 10 meters per second. By the way, sorry over here, but that should have only been 15 meters per second. My eyes playing tricks on me. So the slope, A average, should be 10 meters per second over 15 seconds. So A average is approximately, and we punch a calculator here, 10 divided by 15, that's going to be 2/3, 0.667 meters per second squared. Find the slope of the chord. So find the initial point, find the second point, find the chord between them, find the slope on this velocity time graph, and you have the acceleration. So now we're again on velocity time graph, sorry. And this time we're asked to find the instantaneous acceleration, find A at 10 seconds. So in this case, what we're looking for is we're looking for a tangent line. It says at 10 seconds, so that means we're at this point right here, and I'm looking for a line tangent to that point. Well, a line tangent to that point, in this case, is real simple because it's a straight line. So I'm looking for the line that has the same slope as the line right there. A straight line lies along the tangent path. And if I look at this guy here, it looks to me like he goes about 10 meters per second approximately. I'm not quite at the right place here. Let me move my thing. So about 10 meters per second. And he did that over 10 seconds. That means this distance right here. So A would be 10 meters per second over 10 seconds. So the acceleration was 1 meter per second squared. Now that does not tell you that the velocity I know is positive. The acceleration is positive, which means the velocity is increasing. Up here, the object is moving at 15 meters per second. So going further and further away, let's say from x equals 0. But if you were looking at this point, it would have no acceleration. This would imply this is a constant speed. It wouldn't be at rest. It would be moving at 15 meters per second. But it would not be accelerating. Anytime you have a straight line, for instance, in this region, you could apply the kinematic equations. But you couldn't apply it from 0 to 20 seconds because the graph doesn't stay straight. You could apply it for the first 15 seconds. You could apply it again with the different acceleration for the next 5. You could apply it over here. You could apply it there. But you'd have to break the problem down if you want to use the kinematic equations into regions in which the velocity time graph is straight. Now, the thing could have a curved graph and there'd be no regions where it's straight. Then the kinematic equations would never be true. Anyway, this is how to find acceleration from velocity time graph. Now we deal with velocity time graph to find an object's displacement. This is a little different than what we have with position time graph. We actually have to find the area under the curve. So let's say the problem says find the displacement of the object from t equals 0 seconds to t equals 20 seconds. Well, all we have to do is we have to go out here to 20 seconds and draw us a line like right up to here. And we look at this shape, and I don't know the area, that type of shape well, but I tell you what I do know. It looks to me like I can break this up into two shapes. There's a rectangle here and a triangle. So I'm looking for the area of that, and I'm looking for the area right here. And I want to add those two areas together and get the displacement delta x. So delta x is equal to the area of the rectangle, which is 5 seconds, times the height of the rectangle, which is 15 meters per second, plus the area of the triangle here, which is 1/2 times 15 seconds times 15 meters per second. Notice that the seconds cancel. I'm in the units of meters, as I should be. Seconds cancel here. I'm in the units of meters. So delta x, 5 times 15, that's 75 meters, plus 15 times 15, that's 225 divided by 2. So we have 15 squared divided by 2, be about 112.5. And we have to add those two together, and we find that's about 188 meters, or approximately 188 meters. So if you want to write that in vectors, that's simply 188 meters I hat. By the way, it is impossible to state the position of the object. All you can find is the displacement. To note the position, I have to know where the person called x equals 0. That is, they have to tell me the initial location of the ball at t equals 0. All right. You don't have to start at 0. You can start from any other place. For instance, we start at 5. Then we would cut off this little piece right here. And so we would have probably find it easier to find the whole triangle and then subtract this little triangle to find the rest of the area. All right. Anyway, idea is find the area under the curve of velocity time graph to get displacement. So now we have the last thing on a velocity time graph. We're asked to find the average velocity. I warn you very carefully that only in the case where the graph is just a straight line, it has no other shapes, can you take the final velocity and the initial velocity, add them together and divide by 2. In general, that doesn't work. So for instance, if we only cared about this part of the graph up to 15 seconds, I could take the final velocity 15, add the initial velocity 0 and divide by 2, and I get 7.5 right in the middle. But for anything else, that will not work. What you have to do is use the definition. And the definition of average velocity is the displacement divided by the time. So what you do is do what we did from the last part of the video. We found the displacement, for instance, over this problem from 0 to 20 seconds, which was the triangle plus the rectangle. It gave us 188 meters. And then we divide by the time, which is 20 seconds. So V average for our problem is approximately 188 meters over 20 seconds. So V average is approximately 9.4 meters per second, assuming that I did the math correctly. Remember, to find the average velocity, you've got to first find the area in the curve, that is, find the displacement, and then divide by the time. So a lot of time, again, they don't ask for a displacement, they ask for average velocity because they can kill two birds with one stone. Anyway, this covers everything on velocity time graphs.